Okay, this is lecture 14, the very first lecture after our midterm examination. As I told you before, uh, tomorrow night we will have an online session to explain the answer of our previous midterm examinations, and please join if you are interested. And we will just keep our discussion about PN junction. Okay. So in the previous lecture we have discussed about depletion with approximation at equilibrium. So we will keep the discussion from now on. So one thing we have to be able in this study is drawing an energy band diagram. So previously we were able to set the values of EC and EF at the two ends. Here we have P-type ends and N-type ends. Its position, so EC position or EV position are given from our doping density. If we have P-type density, then our Fermi level should be very close to valence band maximum, and if we have N-type region, then our Fermi level should be very close to the conduction band. So at equilibrium, so please note that at equilibrium we have a strict condition of existence of Fermi level, and that Fermi level is regarded as the reference energy which is uniform or global all over our system. So that's the reason why here, even though we have no idea about what is the exact shape of a conduction band minimum or valence band maximum, but still we can find that there exists certain difference in energy levels. So here we have more energy and less energy from the reference energy Fermi level. So up to now we have discussed about this part, and after that we have introduced the depletion approximation. So in the depletion approximation, your field strength is given as in this triangular shape, because starting from this starting point of our depletion region and end point of this depletion region, we have a constant net charge density. So therefore here we have a linearly increasing electric field and linearly decreasing electric field. If this is electric field, yes, magnitude of electric field, since electric field is obtained as just the first order derivative of our electrostatic potential, if we are considering the shape of our electrostatic potential, then we can just integrate this electric field once more. So here you can see that this electric field follows just piecewise linear function. So you will immediately understand it will become just a piecewise parabolic function. Of course, we have to introduce the continuity of its first order derivative. So that's the reason why in this case you can see that they look quite smooth. So it just looks like parabolic curves, because its first derivative should be a linear function. So second order derivative should be just finishing. So now you have this form here. Yes. So so in between, actually the form of this conduction band maximum or valence band minimum actually it is difficult to draw by our hands, because exact value should follow the numerical values. But important point is, at least in this case, although we have no sufficient idea about actual shape of EC or EV, but we can see the difference of a conduction band minimum. It means that from the viewpoint of electrons originally located in this area, n-type region, so it would be quite difficult to overcome this given potential barrier. So here we have a lot of electrons. For example, if we have introduced 10 to the 20 per cubic centimeter, yes, then we will have that so many electrons in this part. However, that excessive large number of electron density is compensated by this energy barrier. So now think about this one. So we have Seoul City or Gwangju City anyway. Here we have so many persons. So population is about several millions. There are million persons. But think about certain mountain here. Here we have a certain mountain, and its height is about 1,000 meter high from the sea level. Then how many person can you find every day? So the number would be much smaller than that found in this ground level. So quite similarly, since we have potential barrier here, although we have many electrons here, but it would be very difficult to overcome this potential barrier. So that's the reason why in general we have so severe density difference in this part. For example, let's say if we have, for example, 10 to the 17 per cubic centimeter, then expected density of our electrons here is just, for example, 10 to the 3 per cubic centimeter. And here we have 10 to the 20 per cubic centimeter. And the distance is just about 100 nanometer. So what happens? The density, the gradient of our density is almost quite close, 10 to the 20 per cubic centimeter, which is occurring in just 100 nanometer. That is really steep gradient in this case. So if we consider only if we consider only diffusion component of our electron flux, then we must consider quite strong, really strong diffusion current from this n-type region into the p-type region. However, at equilibrium, it is not allowed to have any kind of current flux. So how can we prevent such kind of net movement? Net movement is just prevented by this potential barrier. So now you can see, simply speaking, at equilibrium we have a delicate balance between our drift component and diffusion component. Actually, this diffusion component is ever existing, so this guy is the driving force, and drift term just to prevent its existence, the net current flux in this case. So please have a look at this view, and once if we just break the perfect balance between drift and diffusion, then what will happen? That is the point. Since we have very strong diffusion term. If we have a slightly weaker drift term, then we will see this drift term. And on the other hand, if we try to increase this drift term a little bit, then we'll see later it is not that easy to increase this drift term. Okay, so I think that that's all for equilibrium case. But before finishing our discussion on the equilibrium case, let's have a look at just a numerical solution obtained from our calculation. So here we have a typical example in this course, 10 to the 20 as a n-type doping density, donor density, and 10 to the 17 as an acceptor density. So please note that this is p-type reason, and over there here we have n-type reason, so 10 to the 20. But you know that since p-type has a lower density, actually, you know, all of interesting phenomena called as depletion occurs only in this p-type region. So that's the reason why I have not drawn this n-type region. Of course, in n-type region we have a very short, really short depletion, but depletion length would be just 1/1000th of this p-type region depletion width, so we cannot see it quite clearly. So please have a look at this number. This is 10 to the 17. Why it is 10 to the 17? It is because our acceptor density is given as 10 to the 17. So if we go to further deep into this p-type region, then we expect that hole density is just constant. So, you know, now this part is the really boring part. So this is called as quasi-neutral region, and we have just quite a close situation to the local equilibrium case. But if we are going into, or if we are approaching to the metallurgical junction, the junction point between n-type region and p-type region, then we can see sudden drop of our hole density. So if we exactly follow the depletion approximation, then how does it look like? The hole density just assumed as this way. Up to certain point, the starting point of our depletion region, hole density is just quite close to Na. After that, once this depletion region starts, then we assume that almost immediate depletion of hole density, and beyond this point there is no hole at all. That was the assumed profile of our hole density. Since we have introduced such a kind of a simplified form, so now we can see that that charge density is just piecewise constant, and after that we were able to integrate it once to calculate the electric field, twice to calculate the potential. However, please have a look at this red color line. This is the realistic one, and this is numerical calculation result. And how does it look like? You can see that actually, although we have assumed the perfect and abrupt change of hole density, unfortunately the realistic solution shows certain margin or length margin to follow the assumed behavior. For example, Na in this quasi-neutral region and 0 at this depletion region. So this length scale is corresponding to the Dubai length we have already considered in our previous lecture. So we have to understand depletion approximation cannot be a perfect approximation. However, compared with the length scale, like for example in this case this is 100 nanometer long, and how long is it? It is much shorter than the entire length scale. So that's the reason why anyhow it can give us more and less reasonable result for our PN junction. Okay, if you have any question, then please let me know. I expect there's some questions from students at this point, but yes, so if you have any question, then please anytime let me know and interrupt me. So now we go to the externally biased junctions. So externally biased junction means that simply we apply certain voltage to our anode or cathode. So since cathode that is connected to our n-type region, and anode is connected to our p-type region. So if we say cathode is grounded, for example, we cathode equal to 0 volt, then positive value of anode voltage, then we call it as the junction is forward biased. And if we have the condition of anode voltage lower than cathode voltage, then this is called as a reverse biased PN junction. That is quite straightforward. Of course, this can be also the case. For example, yes, you have applied cathode voltage 0.5 volt, positive one, and actually your anode is just grounded. Then is this device or is this junction in its forward mode or reverse mode? So now cathode anode, we have to care about the relative distance or difference between anode voltage and cathode voltage. Although here we have different numbers, but the relative voltage, anode voltage, is just minus 0.5 volt. So we understand this one is really in its reverse bias mode. So now think about this case, N MOSFET and P MOSFET. Here now you have our N MOSFET. Here we have a P substrate and its source is grounded. Yes. And here we have substrate. Yes, what is it? And now we have a certain drain voltage. This drain voltage is now positive. For example, let me say that 0.7 volt, let's assume. Then now our p-type substrate is grounded, biased to 0.0 volt. Then please try to estimate the operational region for this PN junction. So especially source to drain to substrate junction. So is it in the forward mode or reverse mode? So p-type region, that is just zero bias, and here we have positive bias for our n-type region. So now we can say that it is in its reverse bias mode. Okay, so now think about this one. Here we have a substrate. Now I want to apply 0.2 volt or minus 0.2 volt. Please think about the operational mode of these two cases. It really happens in real devices. Sometimes we apply non-zero voltage to our substrate to control the threshold voltage. So now think about this one. If we have 0.2 volt and 0.7 volt for our drain, this drain substrate junction is still minus 0.5 volt difference from the viewpoint of anode voltage relative to the cathode voltage. And here we have 0.9 volt still. So yes, there is no problem, but potentially one of them makes some problem. What is the problem? Here we have drain to substrate junction. However, at the same time we have also another junction between our source and substrate. Yes, now we have 0 volt, and if we have positive 0.2 volt for our substrate, then what will happen? This PN junction is placed in its forward mode. Then everybody in this classroom now understand, if a PN junction is placed in its forward mode, it starts to conduct the current. So it means that there occurs certain current conduction between this source and substrate. This is not a desirable situation. The only desirable situation between these contact is just current conduction between source and drain. This is designated current conduction path we wanted to have, and any kind of current conduction between this source to substrate or drain to substrate, it should be minimized. So this is a very bad situation. So I wanted to say that in the case of N MOSFET, the allowed substrate voltage is always what? Always a negative substrate voltage can be applied. It is safe. If you apply negative voltage to your p-type substrate, always it strengthens the amount of negative reverse bias voltage. But if you introduce positive substrate voltage, then potentially it places your junction into what? Into the forward mode. That is a very bad situation. However, this is all related with P and MOSFET, and now we have its dual device called as P MOSFET. In the case of P MOSFET, now here we have P and P substrate, P-type source and drain. Now we have N-type substrate. The polarity has been inverted, so please think about the value of your substrate voltage which can be applied to your P MOSFET. Okay, so anyway, I'm emphasizing this one because sometimes the students are confused with its polarity. So positive or negative, which one is allowed? So please try to understand this one. Actually, in the MOSFET, your PN junction should be placed always in its reverse bias mode. So please avoid the forward bias mode in your PN junction, because you wanted to use the MOSFET as a MOSFET. Basically, here you have N plus, N plus, and P plus region. So if you have any kind of current conduction shown here or this one, if we have this kind of a current injection from source or drain into this P-type substrate, then if you have already studied a device called as a bipolar junction transistor, then you can immediately understand this is nothing but just bipolar junction transistor. So have you studied the bipolar junction transistor in your previous course? Some of you know. Okay, there is another kind of transistor called as a bipolar junction transistor. Typically it has three different regions, so doping regions, N plus, P, and N plus. So exactly same with our current MOSFET structure. However, in the case of MOSFET, this current path is not a desirable path. The only desirable path is just following the surface between top surface between silicon and oxide here. However, if we activate this path, then actually the MOSFET can be working as a parasitic BJT. This is really bad situation, so we have to avoid this one. So please understand. By the way, let me just come back to our main slide. Okay, so I think that everybody understand the meaning of forward bias and reverse bias junction, and now just to consider boundary conditions. So here we have a boundary condition for electrostatic potential. If you apply certain bias voltage, then it is just added to your potential. Yes, it's not that difficult. Let's say that if you apply 0 volt, let's say that your electrostatic potential was, for example, 0.5 volt. Let's assume just. Then now you apply, instead of this 0 volt, now you apply 1 volt to that contact. Then my question is, then what will be the electrostatic potential at that point? Since you have just increased the potential, applied potential by 1 volt, so the answer is just clearly 1.5 volt. Why we have 1.5 volt? Because applied voltage is just added to our equilibrium potential. So now we have 1.5. So it's not that difficult to understand. Also, we have two more quantities. What is two more quantities? Quasi-Fermi potentials. We can define electron quasi-Fermi potential and hole quasi-potential. And you know, in this case, also it is simply given as applied voltage. So simply speaking, think about this one. When you have applied voltage equal to 0 volt, then what will happen? It means that if you apply 0 volt, then your electron quasi-Fermi potential and hole quasi-Fermi potential becomes just 0 volt, and it is corresponding to the Fermi level. Simply speaking, if you apply 0 volt to everywhere, then your system, your quasi-Fermi potential becomes just the Fermi potential at equilibrium. So it is consistent with our previous definition of a Fermi level. So why we are talking about this one? It is well used in our new drawing in energy band diagram. Now we have to consider the situation with non-zero applied voltage. Now it is no longer possible to define Fermi level. At equilibrium, we were able to draw a horizontal line and say that, oh, this is a Fermi level, so that will be the reference. However, now it is no longer possible. But fortunately, now we can say that although we cannot define Fermi level, but we know the deviation from that energy level. For example, let's say that anti-blazon we have applied just 0 volt, then no change at all. Good. And in the case of a p-type blazon, let's say that we just applied, for example, 0.1 volt, then what will happen to our case? In this case, now since this is just 0.1 volt, and when it is converted into energy, then we must multiply minus Q, because we are now taking the electron picture. So electron has minus polarity for its charge, so we have to calculate minus Q times 0.1 volt. This is corresponding to just minus 0.1 electron volt. So simply speaking, here our conduction band and valence band also downshifted by amount of 0.1 electron volt. So now we can draw in that way and that way. So everybody can understand now the potential barrier seen from this anti-blazon can be reduced by amount of just 0.1 electron volt. So if we apply positive 0.1 volt. So are you all with me? Okay. So now you can see that if we apply positive bias, then barrier height will be reduced. However, instead of this positive 0.1 volt, let me just consider the opposite case, like minus 0.1 volt. So although this is minus 0.1 volt, when we convert it to the electronic energy, then it is corresponding to positive 0.1 electron volt. So it is just upshifted. So now you think that your conduction band level is upshifted. Now here you have the new conduction band level. So the barrier seen from, once again, seen from this anti-blazon would be even higher than the equilibrium case. So it would be much more difficult to overcome this potential barrier. So are you all with me? And I wanted to say one important thing. So I hope that now most of you can understand this one quite clearly, but there is one point that I have not talked about up to now. Here you can see the position of quasi-Fermi level. Quasi-Fermi level is also shifted by minus Q times applied voltage. So now you can see that this point and that point, since we have assumed that cathode region is just kept as 0 volt, now it is just attached to our previous Fermi level. But now here we have a little bit shifted, downshifted version when we have forward bias voltage. So it means that from the viewpoint of our electrons located here, now Fermi level just determines the driving force, its gradient. If we have gradient of quasi-Fermi level, it means that there will be a flux. So do you remember this one? For example, Jn is just proportional to the gradient of electron quasi-Fermi level, and also whole current density is proportional to the gradient of whole quasi-Fermi potential. So simply means that if we have a slight difference the end-to-end value of quadriform level here and there. It means that we will have current conduction in this state. Okay. My final comments on this diagram still remaining. You can see that I have drawn this conduction band and balance band diagram up to here, up to some point deep into this substrate. So now you can see that maybe somewhere here we have the starting point of our depletion layer. But please note that I have drawn the quadriform level only at contact. So let's say what we can say certainly in this stage is just at contact, both of electron quadriform potential and hole quadriform potential will follow applied voltage. Just nearby that contact, what will happen to our electron or hole quadriform potentials? Up to now, we have no idea, and I think that since you have already studied this course in a previous case, actually it has a certain gradient. So now, at this point, we can draw both of electron quadriform potential and hole quadriform potential. However, when we go into the p-type region away from the contact, then now you can see that the behavior of your hole quadriform potential and electron quadriform potential are different. They are separated. Also, even in this case here, you can see that at this point, both of them is equal to 0 volt. However, if we go too deep into this n-type region, then now you can see that electron quadriform potential does not change much. However, your hole quadriform potential changes considerably in this n-type region. Simply speaking, only minority carrier Fermi potential changes in some point, so we will discuss it later. But anyway, we must understand this situation. Quadriform level, although here conduction band level and balance band level, which is corresponding to the potential is almost constant in this way, and almost constant in this way. It means that there is no such a high drift component. However, still we must have what? We must have the current. Then you can see that the current is supplied in this case by the action of diffusion component. Electric field is 0, but still we need a non-zero current density. How can you generate non-zero current density? The only way is to introduce density difference and introduce diffusion component. Okay, so if you have any question, then please let me know. And now it is quite easy to understand. At non-equilibrium, the depletion width will be a little bit different, because now we have, instead of this built-in potential, if we apply positive bias to our anode, then built-in potential will be reduced, and if we introduce negative potential, then potential value will become even higher. So now you can see that when you calculate this depletion width, instead of built-in potential, which is valid at equilibrium, we can just introduce a little bit modified one. So yes, you can add this minus applied voltage into it. So I have just drawn this typical example. N-type reason is 10 to the 20, and p-type reason is 10 to the 17, and here we have anode voltage equal to 0 volt. Then you know this is about 110 nanometer. After that, if we go to positive anode voltage, it means that now we have reduced barrier height, reduced potential barrier, and therefore relatively small amount of depletion can sufficiently supply such kind of a potential difference. So that's the reason why we have reduced depletion width. On the other hand, if we go to this negative value of anode voltage, it means that we have even higher potential difference. So in order to supply that high potential difference, we need more charge. Then how can you generate more charge? The only way is just to expand the width of our depletion layer. So that's the reason why we have even higher value for depletion width. Okay, so it's not that difficult, and I think that everybody know this one. PN junction is working as a rectifier, but in my opinion it is important. This one, this is the very first example of a non-linearity in our electronic device. So please think about the origin of this non-linearity. I mean that when we consider a resistor is regarded as a linear circuit element. So for example, let's say that IV characteristics, and if you apply certain V naught voltage, then let's assume that you have I naught voltage. Let's assume. Then question is, if you apply minus V naught voltage to your resistor, then what is the expected value of your current? Obviously, you know that this would be minus V0. So that is quite natural. So just changing the polarity of your applied voltage makes the final result just inverted without changing its magnitude. However, as you know, this PN junction, this is not the case. Although we have certain amount of current conducted at positive voltage, however, if we go to the negative voltage corresponding to the reverse bias mode, then what is the expected current value? The current value will be just quite close to 0. So simply speaking, in the case of a resistor, you just care about the magnitude, and the value just the sign of output current just follows the sign of your input voltage. However, in the case of this nonlinear component called as a PN junction, you have clear distinction between positive bias and negative bias. And why do we have such kind of a non-linear behavior? What is the origin? The origin is maybe somewhere here I wrote it but deleted it here. The origin is the structure of our PN junction. So please note that at equilibrium, I'm just repeating my previous argument once again. At equilibrium, we have zero current. Yes, we have zero current. But please note that that vanishing current was not obtained quite naturally. That was obtained by delicate balance between our drift term and diffusion term. And due to the structure of a p-n junction, actually we have really strong diffusion component, and that was just compensated by our drift term. So I'm saying that let's think about this wall case. Wall and a person, and a person is just pushing it this way. Yes, nothing happens. So now think about this case. Here we have a wall, and this wall is quite strong. However, this human, this person is also almost a demigod. So now let's say that this guy just to push the wall quite close to the limit of breakdown. So if he or she just push it a little bit, then this wall will be broken. Now think about that situation. So in this case, push it large hand, and if we slightly increase the power pressure given by this giant, then this wall will be broken. So slightly positive value of the pressure will make just a broken wall. However, think about slightly less powerful pressure, same amount. However, slightly less pressure on it. Then what will happen? In this case, nothing happens. So are you all with me? Or think about this one. Here we have certain structure. Here we have a certain structure. And we have a ball. I have drawn one long profile, so let me just draw more reasonable one. Let's think about a landscape like this, and we are here. We have a ball, and if we just push our ball into this way and that way, please think about the movement of our ball. What will happen? If we slightly change the position of this ball into, for example, 1 meter, then that will generate a really drastic movement of our ball. And if we just push the ball toward the left direction, then although we have applied the same amount of displacement, then nothing will happen. The ball is just there. So let me just come back this concept. Here we have drift and diffusion. They are perfectly balanced at equilibrium. However, the driving force is really drift, and this diffusion, and drift is just working as preventing mechanism for current conduction. So now if we have the case like a slightly weaker drift, then we will have a strong diffusion current. However, if we increase the value of this drift term, then there will be nothing more. So that is the reason why we have non-linearity. So I'm not quite sure I have delivered the main point, but we have two different current conduction mechanisms, and in the p-n junction they are perfectly balanced at equilibrium, but depending on the polarity of your applied voltage, this balance is just unbalanced, and that's the reason why we have two different behavior of a p-n junction. So everybody now understand this is 0 volt, and for forward bias, yes, we have sharp increase of current, and if we go to negative bias, reverse bias, almost we have no current conduction. So please, although I have drawn it as a linear scale, but you should be able to draw the same graph with semi-logarithmic scale. I mean that your applied voltage is still in its linear scale, but for example, you can draw log 10 of your diode current, for example, anode current. Then you should be able to draw this one. Okay. So now, first of all, sorry about this graphs. So usually I have, up to now, I have introduced some examples like p-type and n-type placed here, and the density was 10 to the 17 and 10 to the 20. But in this slide and for a few more slides, instead of this pn, unfortunately I have introduced n and p structure, so position of n and p are swapped, and intentionally I have introduced comparable values for doping densities. Donor density is also just orders of 10 to the 17, just for visualization. So please note that in reality we have no such kind of a p-n junction because they are more or less comparable. This is not the case. In reality, almost every time we have just one-sided junction. One doping density is much higher than the other one. So please understand this is for just educational purpose. So now we are drawing the space charge. So what is space charge? Nothing but just our rho, net charge density, as a function of a position. What? This is our x. Now you can see this red curve. This red curve is corresponding to the equilibrium case, and you can see that this is junction, metallurgical junction, and now you have this scheme. For example, this is 0, so beyond this point we have a net positive charge, and below this point we have a net negative charge. Then what happens to this one? Now across this junction, in this n-type region we have a net positive charges, and here across this junction, in the case of our p-type region, we have a net negative charges. Okay, minus. Of course, the amount of these two charges are the same. Why? If we don't have a perfect balance between these two charges, then actually all of this entire structure will be charged and it will generate a certain electric field all over the universe. So it is not possible. There will be certain screening effect. So now we have this one. But point is, this is just a starting point. In this slide, I wanted to emphasize the difference between this 0 volt case, the reference point, and slightly deviated point minus 0.5 volt. So in this blue case, we have introduced a negative voltage into our system, and now this blue curve shows a new spatial charge, and also this blue one shows a new space charge. So please try to interpret this diagram. When you apply negative voltage to your anode, then now you have more positive charge in this n-type region, and now you have more negative charge in your p-type region. Okay, and that, so let's say there is a certain structure, and say here we have one is grounded, and previously we have applied 0 volt, and now we are saying that when we apply minus 0.5 volt, then we have additional negative charges and additional positive charges. That is the situation seen from these two curves. So I'm saying that, I'm not saying that in this case there is no net charge, no net charge. I'm not talking about this statement. Even at 0 volt, we have certain amount of net charges accumulated or collected at the junction. So do you remember? So previously in this p-type region there was a net negative charge and net positive charge. I'm not talking about this built-in value. What I wanted to say is, when we make the difference between 0 volt and minus 0.5 volt, there occurs additional charge collected by this additional voltage. So I'm not saying just charge itself, but I'm saying the difference of charge induced by what? Induced by difference of applied voltage. So now you understand, if we have this kind of form that is corresponding to a differentiation, and that differentiation will give us a certain quantity. What is the dq over dv? That is corresponding to a quantity called as capacitance. So now we can think about a capacitance assigned to a p-n junction. Okay? But please note that once again this relation is related with the difference of charge, okay, at the given bias, whether that is positively charged at a certain contact or negatively charged, that is none of our interest. We are now talking about if we apply additional voltage, how much charges can be collected by that action. that additional voltage that is considered in this capacitance calculation. So I think that here we have a little bit of a calculation, but you can do it. So let me just read once again. When additional voltage is applied to the n-type region, so now the system is driven to its reverse bias mode, then we have additional positive charges in the n-type region. So if you apply positive voltage, then you have additional positive voltage, and if you apply negative voltage, then you have additional negative voltage. Good. Think about this one. I'm giving you a counterintuitive example. Let's say that here we have ground, and say that there is a certain DC voltage. Then now you just increase your DC voltage by amount of 0.1 volt, and let's say that there was certain amount of charge Q and negative charge Q, and now since you have applied just 0.1 volt additional positive voltage, now what you can expect is additional positive charge. So you are now assuming that this way. If you apply additional positive charge, then for that contact you expect additional positive charge. That is quite natural. However, in our system, in our electronics, there is some cases we have no longer having the positive charge response. So we have something like delta Q equal to negative. I'm not kidding. This is a serious, really serious research interest in nowadays. So they are now trying to use this property for our realistic electronics. But anyway, this is really matter of our research, and at least in the case of a mass production device, still we are considering positive capacitance. So if you apply additional positive voltage, for that contact you expect additional positive charge. So now let's try to calculate this capacitance. How can you calculate this capacitance? Now you apply additional anode voltage. Then please try to calculate the amount of charge increased by this one. So I'm afraid, because some of you are confused with the different signs and polarities. Please don't be confused. For example, let me just draw more concretely. Now say that here you have a PN junction, although I have drawn it as a capacitor, but let's say that this is a PN junction, and you have applied 0 volt and 0 volt. Let's say that this is your P-type region and this is your N-type region. Then what happens in this case? Even though we have applied 0 volt, but from our previous understanding, here we have negative charges collected and positive charges collected. Are you all with me? This is the situation of our PN junction at equilibrium. Even although we have not applied any voltage difference between cathode and anode, but by action of our PN junction, we have a certain negative charges in p-type region and positive charge in p-type region. Then is it related with capacitance? Actually not. Capacitance is once again the concept originated from difference. Now please have a look at it. Now we want to consider this case. Now we have still 0 volt and we have applied V applied, and let's assume that this is a positive value. Then if you apply positive value, then what you can expect is now in its forward bias mode, depletion width becomes narrower, so amount of charge collected in this PN junction will be reduced. So instead of 4 symbols, I just drawn 3 symbols in order to say that we have less amount of charges. So now please try to estimate the dq and dv. What is it? In this case, what is dq? This q is the charge collected in its p-type region. Then we had 4 different negative symbols, and now we have 3 different negative symbols. So simply speaking, we have net positive change in its net charge density. So it sounds a little bit weird, negative and difference, but please don't be confused. Its net movement or net change is positive, and of course here we have applied positive value, so difference of voltage is also positive. So C is regarded as the positive quantity. Okay, then once you understand, then now you can easily understand this one. What is it? This is corresponding to the p-type side length of depletion layer. Of course here we have a depletion layer with, however, that is divided between or shared by n-type region and p-type region. If we have a higher doping density, higher donor density, then actually the depletion width in the p-type region becomes longer. So that's the reason why here we have Na instead of Nd instead of Na. So after you calculate all of these calculations, now you have surprisingly simple value or expression like a CD equal to epsilon over WD. So please note that here CD is not in farad unit. It's not. It is, please note that this is permittivity. Permittivity has the unit of farad per centimeter, and here we have also depletion width, which is in the length scale. So CD, usually CD is given as just farad per square centimeter per area, unit wise or area wise. Farad is drawn here. Of course, if you wanted to really calculate the capacitance itself, the farad quantity, then you must multiply the area of your PN junction. Please, up to now we have just considered one-dimensional structure called as PN junction. However, since this is three-dimensional structure, actually we have two other direction that let me just consider here. This is the direction written as x. So up to here we have n-type region, and beyond that point we have a p-type region. We have studied in that way. However, in reality, since this is a 3-dimensional structure, we have a certain dimension and dimension. Yes, this is the actual structure, and the area of this structure should be multiplied to calculate the real capacitance written in farad unit. My final comment is related with this physical interpretation. So when students first see this result, CD equal to epsilon over WD, they sometimes feels quite comfortable because the expression is quite simple and easy to remember. But please think about this one. We have spent a lot of internal calculation and derivation procedure, and the result is so simple. Why it is so simple? It is related with, although we have spent quite a lot of time, this C is always related with the difference. This is not collecting the charge itself, but it is just considering the additional amount of charge obtained by additional applied voltage. So we have no idea in current situation. Let's say that this is our DC voltage right now. We have no idea about Q distribution over this area. But point is, one thing we can say certainly is, if we apply DC voltage plus 0.1 volt, and if we have to collect more positive charges here and more negative charges here, then that positive charge or negative charge will be found at this point. At this point, we cannot generate more positive charges here or there, because our depletion layer already contributed completely its capability. All of movable our electrons holes are depleted, and this one, in this depletion layer, we have no further ability to change the net charge density. They are just depleted. Then the only capability to move or get more charge or get less charge is now remained only at this point, and the distance between these two active points is given as depletion width. So simply speaking, although it is a non-linear system, but the capacitance evaluated from the difference between 2 points is simply seen as just capacitance or dielectric material separated by WD. So that is the reason. Okay, I will stop here, and if you are interested with your midterm examination, please join our tomorrow office online hour. Thank you.